seventh lecture for Introduction to Nuclear Engineering, and we will learn about fission today. This lecture today will be very much interesting because you will learn something new about fission interaction. Now, this is fission. So when uranium-235 captures neutron, it temporarily becomes uranium-236. That is unstable fission of unstable. So it undergoes fission spontaneously. Okay. So and the fission fragment we call fission fragment or fission product. So there is a particle that produced after fission. So uranium-235, 236, it just disintegrated into 2 or 3 fission fragment. So normally, as we learned before, fission fragments are neutron rich. So many neutrons. So in order to be a stable element, it should undergo some kind of radiation emission. By emitting something, it becomes stable element. So I told you heavier elements have neutron-rich behavior. So when it decomposes into 2 or 3, the fission fragment has more neutron than needed. So it is normally unstable element, and it undergoes radiation emission. So sometimes it emits delayed neutron, sometimes it emits gamma, sometimes it emits alpha. So in that way, they are losing their nucleons, and by doing that, the unstable fission fragment become stable element. So this is an example. So neutron plus uranium-235 undergoes fission. So one of the fission fragment, it undergoes beta minus decay 1, 2, 3, and ultimately it becomes stable atoms. So this is the way where the radiation comes. Now, people say fission product activity is so it is a statistical nature. So we have to measure that. So there are a number of fission fragments in the nuclear reactor, and they normally emit beta minus and gamma. Why beta? So neutron should become proton. So the beta reaction makes neutron becomes proton. So one way of getting stabilized is to emit minus electron to get to remove neutron and get proton. So it normally fission product undergoes beta reaction and gamma reaction. So time after fission we call T, small t, and the rate of beta emission is 3.8 times 10 to the minus 6 T minus 1.2. That is what we measured, and the gamma ray emission is 1.9 something. Okay, so this is the number we measured, and from this number we will calculate something. Now we will change unit. So 3.8 times 10 to the 6 T minus 1.2. So this is fission product activity. So we would like to change the unit into curie. So 1 curie means 3.7 times 10 to the 10 disintegration per second. So we divide the number with 3.7 times 10 to the 10 to change the unit with Curie coefficient. So the first line shows how we change the unit. And let's think about when a nuclear power plant has been operated with P megawatt summer for 1 day and shut down. And we would like to calculate the total energy generated. So this is just a unit conversion process. But before we go there, we have to understand the notation. P megawatt, and we have very small subscript TH. TH means thermal power. Thermal power. When it is when we consider the electric power, we put the subscript E. So P megawatt thermal is thermal power. And when we convert thermal power into electricity, we have to multiply the efficiency. So normally nuclear power plant efficiency about 30%. So the thermal power, for example, is normally 3 times higher than electric power. So when we calculate how many nuclear fission occurs, we have to know the thermal power. So we use a megawatt thermal. So P megawatt thermal, we have to understand this notation. And so let's convert this energy. This actually megawatt thermal is energy rate, and when we multiply 1 day, then it becomes energy. So we convert this into mega electron volts. So energy total energy equals P times 10 to the 6. 10 to the 6 comes from megawatt, okay? And watt becomes joule per sec, and 1 day becomes 24 hours and 60 minutes and 60 seconds. That gives 3600 sec. And in order to convert this expression joule into MeV, we have to divide with 1.6 times 10 to the minus 13. So we get P times 5.4 10 to the 23 MeV. So this is the energy generated for 1 day operation of P megawatt thermal nuclear reactor. And at one fission, we generate 200 MeV. So if we divide this number with 200 MeV, then we know how many fission reaction occurs. So the number is 2.7 10 to the 21 times P. So this is the number of nuclear fission interaction. And in order to calculate the radioactivity activity after a few days with 2.7 times 10 to the 21 multiplied by P, and you substitute the first line 1.03 10 to the minus 16. So this 2.8 times 10 to the 5 P as minus 1.2 power. This is the fission activity after 1 day operation. Okay? So if you don't understand, just read the text again and again. You have to understand this. Now, total product activity. So for a more general situation, it's like this. In figure 3.13, we operate for large T period and then shut down, and the small T period passed, and then we would like to know how much activities are there. Okay, so we operate for large T period and then shut down, and for small T T period, we just waited. And we would like to know after that how much fission product activities are left. So we are concerned about that. So this is more a general situation. So in the previous page, we learned one day after one day operation, and then past then we will have this expression 2.8 times 10 to the 5. Okay, so we operate we operate large T days, then we have to multiply this expression for large T and plus T. And during the T plus T period, so we assume firstly one nuclear reactor is operated for T plus T period. That is one calculation. And the second calculation is the same operator is the same nuclear reactor is operated for just small T period, and we just subtract it. Then we get this expression. So the integral comes from small t to small t plus large t. Actually, this expression is from 0 to t plus t, and another expression is from 0 to small t. So it is just subtracted. So we put together in one integral small t to t plus t. So that is the expression, general expression for total fission product activities. So in the figure, instead of calculating it operates large T period and it just stayed for small T period. So instead of calculating that, we just calculate one reactor is operating from T plus T period, and the second reactor, the same reactor, operate just for small T period, and just we subtract it, so we get the result. Okay, that is kind of manipulation. So from the activity, in order to calculate the heat, so we have to put average energy of beta ray and average energy of gamma ray. So we insert this expression to the above equation, and we get the following 0.066. So at the end of the day, this expression is important, 0.066. So this corresponds to that means let's look at the last equation. That then means hence or thus. 그러므로 thus. So thus 그러므로. Thus the nuclear reactor operate for large T period and shut down, and stayed for small T period, and the power is 0.066 times the original power, right? So when small t is zero, so it is it means just after the nuclear shutdown. So just after the nuclear shutdown, the nuclear reactor emits about 6.6% of its original power. Now, this is it. In the equation, when we put substitute 1 or 0 to small t, so it shows even after we shut down the nuclear reactor, the reactor emits heat about 6.6%. So it is very important concept in nuclear engineering, because in other plant like coal or liquid natural gas power plant. So in or oil power plant. So when they shut down, there's no more heat generation. Okay, shut down and uh, just extinguish the burner. There's no more heat generation. But in nuclear reactor, even after we shut down the nuclear reactor, we have decay heat. And 6.6 is very large number because nuclear reactor power is very large. So, uh, for example, uh, we have 1,000 megawatt nuclear power plant. Normally, 1,000 megawatt nuclear power plant. So let's think about the thermal power. Thermal power is about 3 times larger than the electric power. So the thermal power is 3,000 megawatt, right? 3,000 megawatt. So let's think about just 6.6% of 3,000. So let's calculate this. Let me 3,000 times 6.6 divided by 100. So it is about 200 thermal power. 200 thermal power. So let's change it to electric power by divided 3, and it is about 66 megawatt. So 666 megawatt is power enough to supply Jeju Island. Okay, Jeju Island. So when the just one nuclear reactor shut down, and the level of decay power is enough to shut down the Jeju Island. So whole Jeju Island. Okay, so the decay is quite large number. So uh, it it is a task of nuclear engineers. So when we have a nuclear accident, even though we shut down the reactor, there is a heat. So we have to remove the heat for a while. But as you see in the picture, the 6.6% of P0 decays exponentially. So soon after, for example, 1 or 2 days, it decreases quickly. Okay, but bear in mind, decay heat is very important thing in nuclear engineering. And this is fission process. And neutron is absorbed to an element, and then it becomes unstable element. And then it decomposes into 2 fission fragment, and 2 or 3 neutron comes out, and gamma ray emission. This is a typical of nuclear fission process. And this is the figure for that. And this is again the figure we are accustomed to. Because fission fragment, again, I'm telling you again, fission fragment is neutron rich. There are some compared to the stable neutron. So it has to undergo radiation emission to become a stable element. Now, I, when I told you there are 2 or 3 neutrons coming out from the fission process, that is quite statistical. So uh, the the size of fission product in the previous lecture we learned double humped curve. So they don't split into even size. So some comes from 100, so the other one comes from 130 something. So there are 2 peaks. So uh, how they split into 2 is quite a statistical nature. So the, that means the number of neutrons coming out from the fission process is again statistical. Some just 2, the other one 3. The other one, 4. Some just 1. So this is quite statistical. So on the average, we can say 2 or 3 neutrons appear from fission process. And it is very important. We have prompt neutron and delayed neutron. So prompt neutron is neutron emitted just after the fission process. More than 99% of neutron are fission neutron, prompt neutrons. And delayed neutron, there is fission product, and after the reaction, for a while, from millisecond to a few minutes, this fission product emits neutron. So this we call delayed neutron. So the delayed neutron is for the uranium-235, 0.65%. So neutron appears immediately, we call prompt neutron. So neutron appears from millisecond to a few minutes after the fission reaction, we call it delayed neutron. And I will not derive the equation today, but later on you will learn the delayed neutron is quite important. So if we have more delayed neutron portion, the nuclear power reactor will be much more safer, because we don't, for example, when we undergo fission, 3 neutrons appear, and this neutron undergoes fission again, and again 3 neutrons appear, then it becomes 9. So this 9 neutron undergoes fission again, and there are 27 neutrons appear. In this way, they undergoes chain reaction. So if we have a large prompt neutron portion, the power increase abruptly. So if we have delayed neutron, we can delay the power increase abruptly. So at the end of the day, we will learn if we have a more delayed neutron portion, so unexpected power doubling will be mitigated. So the portion of delayed neutron is very important for the nuclear safety. Now we will learn this kind of thing from the table. Uranium-233, 235, plutonium-239, and plutonium-241. That is all good fissile material, okay? Fissile. And there is absorption cross-section and fission cross-section. So absorption cross-section is, from this notation, radioactive capture cross-section plus fission cross-section, okay? Radioactive capture cross-section plus fission cross-section. So uranium-235 has absorption cross-section of 680, and fission cross-section is 582. That means radioactive capture cross-section is about 100. So alpha, what was alpha? So that was capture to fission ratio, okay? Capture to fission ratio. And nu was the neutron emitted after the fission. And the eta means neutron emitted per absorption. So all the absorbed neutron does not undergo fission. So eta is always lower than sigma. Eta is always lower than nu. Okay, nu. So sigma A, sigma F, and alpha, we know that expression. That's the next one is not N. This is we call eta, ETA, eta. And the next one is not V, nu, okay? Now, neutron undergoes fission, and sometimes it goes fission, the other one into radioactive capture. And as you know, look at this expression, eta is number of neutrons produced from fission in the reaction and divided by number of neutrons absorbed in the fuel. So there is eta can be calculated by nu times sigma f divided by sigma a. And sigma a is sigma gamma plus sigma f. So when we divide it with sigma f from numerator and denominator, we get 1 plus alpha nu over 1 plus alpha. So alpha is captured to fission ratio. Okay, so table 3.4 is repeating. So we have to understand what is nu and what is eta. Nu, neutron coming out from fission. Eta, neutron coming out from absorption. Okay. So when we have mixture, for example, uranium 235 and 238, so and 238 has absorption cross section, but its fission cross section is quite small. So we just neglect the fission cross section of uranium 238 and only consider the absorption capture cross section of 238. So in this case, neutron absorbed by fuel means absorption cross-section of 235 and absorption cross-section of 238. So that is neutron absorbed in the fuel, and neutron produced in the from the fuel is nu 235 times sigma f 235. So in this way, we can calculate the eta for the mixture. But for the fast reactor means fast nuclear reactor using fast neutron. So thermal neutron, do you still remember the number? 0.0253 eV. So that was thermal neutron, 0.0253 eV. So normally, current nuclear reactor are using thermal neutron to, but in the some nuclear reactor use intermediate energy neutron, or some reactor using fast neutron. So the fast nuclear reactor, the fission cross section for uranium 235 is large. So in this case, we have nu 238 and sigma f 238, because for the fast reactor, the fission cross section of 238 is not negligible. So we have to put the expression here. Okay. Again, we learned neutron spectrum. So this is Maxwellian distribution. Actually, the average mean energy of neutron from fission is 2 mega electron volt. So 2 mega electron volt. You have to memorize this number 2. So for the fission case, the average energy of fission neutron is 2 MeV, and we will use 0.0253 eV neutron. So we have to slow down 2 MeV neutron to 0.0253 eV. So this is large number. So we have to slow down. Slow down means in nuclear engineering term, moderation. So we need moderator. 2MeV짜리 중성자를 0.0253 MeV까지 속도를 줄이기 위해서 속도를 줄이는 감속제가 필요한 거예요. So the prompt neutron spectrum means energy spectrum. So this is you don't have to memorize this number. So this is quite similar to Maxwellian expression. So sometimes we use this equation, but you don't have to memorize this. Now, uh, when we call prompt neutron and delayed neutron, there is a neutron coming out immediately after the fission, and delayed neutron coming out after some time, from millisecond to minute, and gamma the same. Prompt gamma that released from fission, and fission product after some time emits gamma, so that is called delayed gamma. Okay, that's the same concept. So uh, today we learned about decay heat, and decay is quite important because in nuclear engineering and for the safety of nuclear reactor, we have to cool down the decay heat after we shut down the reactor. So as I told you, the amount of nuclear power plant decay heat just after the shutdown is 6.6% of its original power. And for 1000 megawatt electric power plant, the decay heat is enough power to supply Jeju Island. So of course, you understand in Jeju there is only hanyo and gur. No, so there is an industry, there is a university, and there is a factory, and there is a movie, and there is a department store, apartment. So in whole Jeju Island, in order to supply in the whole Jeju Island, we need about 40 to 50 megawatts, megawatt electric, and the decay heat of 1000 megawatt nuclear power plant is 66. So that is enough power to supply Jeju Island. So that means even after we shut down the reactor, we have to cool the decay heat. That is a very important thing. And we derived a 6.6 number today, and we learned about decay heat that coming out from the fission fragment, and we learned about prompt neutron and delayed neutron. We learned about prompt gamma and delayed gamma, and so this will show you a little bit more idea on the fission reaction. Okay, I think this is it. Let's call it a day. Thank you very much. And if you still, at one point, please read the book. I can suggest you like this way. 3 or 4 students get a group and read it together. Read one line and translate into Korean. The next person read one line and translate into Korean, and they each other they can correct their translation. So in that way, don't try to read all the textbook, just some part of textbook. So try to familiarize yourself with reading English book. So I recommend you 3 or 4 students sit together or in Zoom or in online. They just read one line in English and correct their English pronunciation and translate it into Korean, and then try to correct their translation. So this is quite important. When I would like to speak in Korean because for Korean student. So 문제 풀고 답을 안 맞추면 실력이 안 늘겠지. 문제를 풀고 답을 맞춰보고 맞은 문제는 상관이 없는데 틀린 문제에서 내가 왜 틀렸는지를 알아야 실력이 늘어나겠지. 마찬가지로 영어 해석도 내가 해석해놓고 답을 보고 아 이렇구나 이렇게 하고 넘어가는 게 아니고 나는 왜 해석을 이렇게 했을까? 왜 정답은 저건데 나는 왜 해석을 이렇게 했을까?